Our next speaker is from the Trinity collaboration at Georgia Tech, Grace Sheram, and we're going to return our eyes to the sky and think about neutrinos.
Okay. Hi, everyone. My name is Grace Sheram. I'm a postbac at Georgia Tech, and I'm going to be speaking today on behalf of the Trinity collaboration. So Trinity is a neutrino observatory intended to detect neutrinos in the very high energy range from astrophysical sources. So the same things that make neutrinos so difficult to detect, their weak interactions and neutral charge, also make them uniquely suited to deliver data from otherwise opaque regions around the most energetic cosmic accelerators. So in the very high energy range above 1 peta-electron volt, the neutrino sky is still very much unexplored. So instruments that can reach these energies offer a unique way of studying things like jet formation around supermassive black holes, the composition and propagation of ultra-high energy cosmic rays, the evolution of the universe, and new physics beyond the standard model. So Trinity intends to explore this energy range by targeting tau neutrinos in the very high energy range from 1 PeV to 1 EeV via Earth skimming detection techniques. So Earth skimming is when a tau neutrino enters the Earth at a very shallow angle of less than 10 degrees. Then it interacts within the Earth's crust and produces a tau. Then that emerging tau's decay length is just long enough so that it decays in the lower atmosphere, initiating a shower of particles that move faster than light can propagate in the surrounding air, which produces Cherenkov light. So then a telescope situated on top of a mountain and pointed at the horizon can image this Cherenkov light, and the arrival direction and energy of that neutrino can be reconstructed from that recorded image. So here I've included a plot of the all-flavor neutrino flux against neutrino energy with the sensitivity curves of several detection instruments, including the 3 stages of Trinity and these green lines here. So just to explain this plot a little bit more, the lower you go on the plot, the harder it is to actually detect a neutrino, and the larger and or more sensitive a detection instrument you're going to need. So for reference, this blue line here is the sensitivity curve for IceCube and the TeV to PeV energy range. And Trinity, in the full Trinity Observatory in this darkish green line here, targets the energy range just after that. So the Demonstrator, as shown as the top picture there, was deployed on Frisco Peak, Utah in 2023, and science data started in 2024 and has been taking nightly data ever since. So the Demonstrator was built to explore the feasibility of the Trinity concept and to suppress the background that may be recorded during data taking. So the sensitivity curve of the Demonstrator, seen in that uppermost light green line, is not very competitive. It can still detect neutrinos, but the main purpose of the Demonstrator is really to verify the technology and control the background, as well as to develop our analysis chain more so than it is to really detect any neutrinos. So we've started analyzing the data of the Demonstrator, and we're ready to move on to the next stage, which is Trinity 1. So Trinity 1 will be the first of the full-scale Trinity telescopes, and it will have a larger azimuthal field of view, as well as the sensitivity to detect neutrinos. So we're applying for funding for that now and are hoping to get it by 2027 so that we can get the funding for the full observatory by 2031. So the full observatory will be deployed on 3 different sites with 6 telescopes at each one, making up 18 of these full telescopes and consisting of a 360-degree field of view and a core energy range of 1 PeV to 1 EeV. So the Demonstrator is continuing with nightly observations and is operated remotely by a group of undergraduate students at Georgia Tech. So in a data-taking period from October 2024 to December 2025, we observed for 554 hours, recording 735 gigabytes of data files consisting of 1.2 million events that triggered our camera readout at a trigger rate of 1 hertz. For more information on the Demonstrator, I've included our 2 camera and commissioning papers, so feel free to take a look at those for more information. So for our actual analysis, so the raw and merged data that are used in the analysis are stored on OSDF, and then the analysis itself is run on OSPool via HT Condor. So each night of data taken needs to be merged, calibrated, and image cleaned. And all of this together takes about 1 hour per night. I've included a table with the necessary CPUs, memory, and disk space for each of the processes, as well as the number of jobs run per night. So each of these processes are run after each night of data taking locally, which is possible for a single night of data. However, since we're still developing our analysis chain, we often reprocess entire data sets. And for the data set from October 2024 to December 2025, we needed to run an order of 50,000 jobs. So on a single computer, assuming that the entire pipeline is correct, that would take about 152 hours. Instead, we run it on OSPool, which cuts that runtime down to just about 30 hours. So our data volume, as well as the space we need for this analysis, makes the resources provided by OSPool a requirement to run multiple nights worth of data. This also makes it much easier to diagnose any errors that we encounter during our analysis chain, which makes the development of this chain that much easier. So for our results, the number of events we have gets reduced from 1.2 million to just 2,193 events. So the majority that were recorded were caused by fluctuations in the ambient light background, which we call the night sky background, and can easily be rejected by requiring a coincident signal in several adjacent pixels. So the night sky background in all of the camera's pixels is uncorrelated, so the probability of this coincident signal in neighboring pixels is very low. So this picture here shows the camera readout of such an event, and it's important to note that the image is inverted. So the top portion of the image actually represents the section of the telescope that is pointed at the ground, with the horizon shown in that line there. So the signal of each pixel is recorded in photoelectrons and corresponds to the color of the pixel. So the more yellow a pixel is, the more signal it has, and the more blue it is, the less signal it has. So our remaining events, these 2,000 some odd events, were caused by muons interacting with our camera. And they can be characterized into two separate categories: muon tracks and isolated muon-Cherenkov events. So 2,177 of these events were caused by muons directly interacting with the photosensors of our camera and leaving a track-like output. So they're very easy to identify because the muons travel in a straight line and light up successive pixels along their way and leave a pretty clear track. So this diagram shows the different ways that a muon may traverse our camera and the associated output. And so if we see any events that look like these, we can know that they were caused by muons and then discard them. The other 16 events were caused by called isolated muon-Cherenkov candidate events and have a greater spread of signal. So the yellow part of this signal shows the direct muon hit, and then the light blue arc of pixels represents the partial Cherenkov ring that's picked up by the detector. So this can happen when a muon traveling through the atmosphere emits this Cherenkov light, which is then reflected off of our mirrors onto the focal plane of our camera, if a muon is within 50 meters of our telescope. So the demonstrator picks up these partial Cherenkov rings if the muon is moving close to the optical axis. So neither of the events that we have in our data set look like the expected topology of a neutrino event that we've simulated, an example of which is here, which means that we've characterized the entire background. And we're confident that we can reject any non-neutrino events in our future studies, which means that we're ready to move on to Trinity 1. So for our simulations, neutrino events are extremely rare. So we have to simulate hundreds of millions of these events to be able to get the statistics we need for the expected topology, as well as expected properties like energy, emergence angle, distance of neutrino populations with different parameters. Our simulation chain is being implemented right now on OSPool. And so far we have enough simulations for our acceptance calculations and event discrimination. And as we continue to run these simulations, we can develop our detection efficiencies, including calculating our effective area, as well as study our systematic uncertainty from things like atmospherics, attenuation, absorption, et cetera. Simulations are also really important in the design of future telescopes, such as Trinity 1. So each job that we submit runs 200 air showers. And this takes about 12 hours for it to run through the full chain, but has 4 steps for the neutrino interaction and tau decay, the air shower propagation and Cherenkov light, then ray tracing those Cherenkov photons, and finally for simulating our camera response. I have a table here of the necessary CPUs, memory, and disk space for these. Each of the steps of the chain have their own container image that runs that section of the chain, and the submission pipeline submits each of these jobs with the appropriate container image with control over which step of the simulation is being run, either individually or as the full chain. So this is a pretty computationally expensive process, and it really just couldn't be done at the scale that we need without something like OSPool and high throughput computing. So for example, for 100 million air showers, we would have to run 500,000 jobs. And assuming that we can run 1,000 jobs at a time, this would take roughly a year of consistent computing time and continuous job submission for this to complete. So we really need high throughput computing in OSPool for this. So this is a very long process, but the computational and time resources that are provided by OSPool allow us to conduct these simulations efficiently to further drive our research. So to sum up, the Trinity Observatory is an array of imaging atmospheric Cherenkov telescopes designed to detect tau neutrinos in the PeV to EeV energy range via Earth skimming techniques, which will open the door to very high energy neutrino physics. So thanks to OSPool's computing power, we have been able to characterize our full background, and we're ready to move on to the next stages of our experiment. We are implementing our large-scale simulations on OSPool right now, and we really want to emphasize that OSPool is mission critical for experiments like Trinity because they allow us to run our data analysis and do our design studies efficiently. And the necessity of these things will only grow for us as the data volume increases as we move on to the next stages of our experiment. So lastly, I just want to give a big thank you to OSG and OSPool for their continuous support and the resources they provide for us to do our research. So thank you. Any questions?
So it's great to have you here, and two questions. The first one, where is the data? Because you said it's in the OSDF. The OSDF doesn't store data. So where is the data itself stored?
So we keep all of our data on Cedar. I'm not super, this isn't my super area, but we keep it on Cedar, but then we also have our raw merge data.
Yeah, but so you have your own storage where you keep it.
Yes.
And then it's being accessible via OSDF. Yeah, that's your response. Yeah, if this data is disappeared, they will go after you.
Right, right.
And not after.
Yeah, you just keep the data that we're actually like actively being analyzed.
I'm using this also to point out again that OSDF doesn't store data. Okay. It is accessible, used by OSDF. That's one thing. The other thing is you have 500,000 simulation in your last. Any thoughts? I mean, how do you plan to manage the 500,000 simulation? Not the capacity, not the hours, but how do you go about saying, okay, I have 500,000 of these. Let's do it. Any thoughts on that?
That's a great question. I personally don't work on the simulations. I'm more on the data analysis side. So I have a pretty surface level understanding of our simulations. So honestly, I'm not sure, but I can get back to you on that. I can talk to one of our grad students.
Yeah, that's an important part of what we want to understand is what can we do better and different for somebody who wakes up in the morning and says, I want to do 500,000 of these.
Right, right.
Okay.
Hi, thanks for giving the talk. I was wondering, as someone who is a facilitator, what was your biggest pain point in using the open science
Sorry,
pool?
can you say that one more time?
Oh, what was the biggest pain point in
Pain
using?
point, is that what you
Yes.
said? So sometimes recently I had a problem where when I was running the analysis chain for the calibration and for the event cleaning, it just stopped working. I hadn't touched it in a while, so I was like, I'm not sure. I was running a new data set and it just wasn't working for some reason. And I feel like the biggest pain point for me is deciding when it was my fault versus a bigger issue. And so, you know, that turned out to be there was our access point specifically was down at that point and they hadn't put it back up. So it was easily fixed, but I didn't want to be the person who's emailing support and trying to figure it out when it's something simple that I made a mistake or needed something that I could fix easily myself. So I feel like that's the biggest thing because you always like want to figure out exactly what you can do to fix it before you move on to somebody else and move the blame on or something, you know. But so then getting that fixed and everything and working with somebody, it was very helpful. Like I feel like they had a very good support and office hours to go to fix all this, but trying to figure out when it's your problem versus another problem is hard for me at least.
It will be useful for us, and I don't know what the right channel is, that when you have this kind of an experience, to have some kind of back and forth for us to understand, can we provide, whether it's a better error message or another tool, because what you just told me was, okay, I want to use an access point and it's down.
Right.
Okay. I assume that the message that's coming back is not very useful.
Right.
When you are trying to place a job
Right.
and the access point is down. So that is something for the development team to think about, besides giving something cryptic, SCADI not reached or God knows what. So if you can give us these experience or these, okay, I was facing this question, I didn't know how to answer it.
Yeah.
So maybe we can do something better on our end. Okay, Lily?
And sort of to add to what Marone just said, anytime that you run into problems, whether they're your sort of own code, data, or something on our side, it's still useful for you to reach out to facilitation. There's a good chance that if you're seeing it, someone else might be seeing it.
Gotcha. Yeah.
A couple years down the line, another grad student comes by and we're like, oh, I remember seeing that Lily had to deal with this problem. Let's go ahead and go through our notes. This was a solution. So it's a nice way to build that sort of institutional knowledge that we are able to pass down to other generations.
I really appreciate that because when I was emailing with somebody about it and before we knew that the access point was down, she was so helpful and like, oh, well, just try this or whatever. Like, you know, I was nervous thinking about it like, oh, I don't want to waste anybody's time, but she was so helpful and so like, well, have you tried, like, try this and show me what the output is, you know? So it was very, very useful.
Yeah.
Hi, Lily. My name is Rachel Lombardi. I'm the one who's been working with Sophia to kind of help you guys get up and running. So first of all, amazing presentation. It's really fantastic to see into the science instead of just directory names called Trinity. So one of the things that I would love to chat about maybe over lunch is kind of what Georgia Tech could be doing better to kind of make our researchers aware of national resources like the OSPool. Your group happened to fall at a very like niche time where we needed to make changes anyways, and I happened to be the one working with you guys. But overall, I think that there's things that we could be doing better to support, for example, other researchers that have similar, basically running high throughput computing workflows on a high performance computing system. So any ideas that you have for us, I would love to chat about that.
Yeah, for sure. We can totally chat about that.
Thank you.